So hello students, today we will start with semiconductor memories, that is module number 5 from your syllabus. So module number 5 content will be in memories. You will be studying about ROM array. Okay, you will be studying about ROM array. Then you will be studying about SRAM, DRAM, flash memory, then some peripheral circuits such as sense amplifier and decoder. So this is your module number 5. Out of that we will be covering today mostly RAM array, ROM array. Okay, read only memory. So let's start with read only memory. So basically semiconductor memory arrays are capable of storing large amount of quantity or digital information. All right, so the number of transistors utilized for data storage is so much large. So there are some design criteria that will determine the overall storage capacity. So the first design criteria is the area efficiency. Okay, so the area efficiency determine the overall storage capacity. So this will lead to, let me just full screen my screen. All right, I hope it is visible now. Okay, so the first point over here, that is area efficiency. In the area efficiency, that this will determine actually, this will determine overall storage capacity of memory. Okay, and that in turn will be determining the memory cost per bit. All right, so area efficiency of memory array will be number of stored data bits per unit area. Okay, so the next will be memory access time, the time required to store or retrieve the data bit in a memory array. Okay, so that will determine the memory speed. Then we have static and dynamic power consumption of memory array. Okay, normally we prefer for a low power memory designs. All right, so now we will investigate different types of semiconductor MOS memories. We'll discuss in details the issues of area, speed and power consumption of each type of memory circuits. Okay, so let's start with just a preview of memory hierarchy in a, let me just save this document. Okay, let me just show you the brief about the memory hierarchy in a processor. So in a processor, we have on-chip components, data part, register file. This is the processor. The higher away we go from the processor, the larger is the memory size. Okay, so here we have cache memory. Okay, then we have SRAM. Then we have main memory, which is made up of DRAM, and then we have disk memory, which is the secondary memory. Okay, as you can see, the size will go on increasing. It's in terabytes, and the speed with which it operates, the nearer it is to the processor, the speed is the lowest, zero point 0.1 nanoseconds, 1 nanosecond, 10 nanoseconds. And if you go away and away from the processor, that is main memory and all, it will be hundreds of nanoseconds. And closest to the the processor, the size of the memory size is also very less, not so high. Okay, and the cost is the highest. If your the memory is closer to the processor, the cost is the highest. And if you go away, we have secondary memory also, with the cost is very not much high. Okay, so we have to exploit the large amount of memory which is commonly available, and we have to use a sufficient amount of fast, which is expensive memory. Then we have the following are the semiconductor memory types. So it's divided into two types. First is volatile and non-volatile. What do you mean by volatile memory? Anyone? So volatile memory, anyone has any idea? Yes. So what does that exactly mean? It exactly means that the stored data is lost when the power supply is turned off, right? So that means stored data is lost, okay, once the supply is off. Supply is turned off. That is called as volatile memory. So RAM memory, random access memory, we can call it, or it's also normally in literature we call it as a read-write memory. So we have dynamic RAM and we have static RAM, the category of volatile memory. And in non-volatile, what do you mean by non-volatile? Exactly opposite. The data storage function is not lost even when the power supply is off. Okay, so exactly opposite of volatile, non-volatile memory. So in the non-volatile memory we have mask ROM, programmable ROM. Actually this programmable ROM memory is actually called as a volatile memory also, because here we are reading and writing the data also. Then we have EEPROM, erasable programmable read-only memory. Then EEPROM. Under EEPROM we have latest, which is the flash memory, which you might have heard. Then we have ferroelectric RAM, which is used in your credit cards, data cards. Okay. Then we have magnetoresistive. These are all the new types of memories which are coming up. So this is a research topic going on in these areas. Okay. By far, as per the syllabus, we have flash memory, then we have ROM memory, I mean ROM array, then we have DRAM and SRAM in your syllabus. Okay, what do you mean by basically this is actually also called as read write memory. RAM is not only called as random access memory, but it is also called as read write memory. All right, so RAM also means something. It means that it's have a static load. That means we don't have a clock requirement, no clock requirement for RAM memory. So they're extremely fast. They are extremely fast, whereas compared to DRAM, I mean static RAM. So static RAM means, SRAM means static load. We have no clock requirement and they are extremely fast. And DRAM are comparatively slower. Okay, compared to that. So these memories which we are talking about, the mask ROM and the electrically erasable programmable memory, so that means we are able to write also. So these are called as non-volatile read write memory, also called as non-volatile read write memories. Are you understanding? Okay, so read only memory means what? Read only memory means we can only retrieve the previous stored information. We can only read from it. We cannot write or modify the already stored content is not allowed in read only memory. Okay, so is the things classification clear? So we'll go to the next slide. Here is the characteristic summary of the memory devices. You can go through it in details. We have compared DRAM, SRAM, UVRAM, EEPROM, flash memory and FRAM memory. As you can see, here the cell structure consists of one transistor, okay, 6 transistor 60 SRAM cell. Then we have two transistors over here. Flash memory, you have one transistor. Okay, the cell density is pretty high in DRAM. It's low in SRAM, and you can compare the writing speeds. The writing speeds is the lowest, it's the fastest in SRAM, as you can see, and it's the lowest in the electrically erasable PROM memory. Okay, and the cost wise, SRAM is very high, very costly, as so is the electrically erasable PROM, programmable read only memory. Also, it's very costly. Okay, and its application is the main type. We use DRAM as the main memory, then SRAM is used as the cache memory, as you can see here. In gaming machines we have UV EEPROM. Then we have in the ID cards and all, we have EEPROM. Then in memory cards and solid state disk we have flash memory, flash disk. And FRAM is used in the smart cards, right? Such as your credit cards, debit cards, digital camera, we use FRAM memory. Okay, ferroelectric RAM. So these are the few of the comparison points between them. If they ask you in the exam, compare DRAM versus SRAM. So these are the points you need to write, compared to this. So this is the comparison between them. Even we can compare DRAM, SRAM and flash memory. So these three memories we have in a syllabus. So this is the comparison table for them. So you will understand certain things a little later. Okay. For example, why we have the power consumption low and high, why the read speed is so high, what is called as latency. Okay. So all these things we will be covering very soon now. Next, we have an overview of memory architecture. So this is a very basic N is to M memory architecture. There are many, the problem is the many select signals are there. So if you have an N word memory, we have N select signals. So the solution is this decoder. So what's the job of a decoder? So job of the decoder is to reduce the number of select lines, okay, so that the lower number of address lines can select a larger number of select lines. Are you understanding? Okay, so this will reduce the number of select lines. So this is a basic overview of memory architecture. So it's divided into words, word 1, word 2, word 3, and inside the word we have a storage cell where we store the actual bits. Okay, so next we'll go into the detail architecture, memory architecture detail. So we have a bit line and a word line. Bit line and word line short form called as BL and WL. So we have a storage RAM cell where we have a bit line and a word line cross point. Then to access the row in the memory, we have a row decoder. So a particular row address will select the row decoder, and that particular, let's say we want to go to first row. So but that particular address will be activated and it will select one of that possible rows. Okay. Similarly, we have a column decoder. So all the columns are being decoded by the column decoder, and we have a probability here over here we have column addresses. So one of the column addresses will select a particular column. Then to, or we can say to select an appropriate word from the memory row, we use column decoder. Then the sense amplifier, will be learning this later. The sense amplifier will be required to amplify the bit line swing. Okay. And also we have some read write circuits and input output lines. So this will be studying throughout the memory module in more details, but now we'll go to the basic memory array organization. So this is my basic memory array organization. Okay, so here as you can see in detail, here we have main elements as follows. We have number of columns, so we have column number 1, we have column number 2 as you can see, then column number 2 raised to m. So these are all called as bit lines. Okay, what are they called as? Bit lines, or column are called as bit lines. So we have 2 raised to m bit lines. Okay, and these are all columns. So these are the bit addresses. Okay, these are column addresses. Okay, so each memory cell over here, this is my each memory cell. Okay, so we have a cross junction of a row and a column. Okay, so the rows are called as word lines, as we have written over here, word lines. So you have 2 raised to n word lines and 2 raised to m bit lines. So we have written over here 2 raised to m cross 2 raised to n is the memory size, is the size of the memory. Are you understanding? And the cross junction is my memory cell. This is my memory cell. And total we have 2 raised to n cross 2 raised to m is the total size of the memory. Okay. So when you want to access, so each memory cell will store 1 bit of binary information. So here we can write very important information. Each memory cell will store, as you know, the computers inside the processor will all work on binary information, ones and zeros. It doesn't understand the decimal number system. So it will store either the information or the memory will be stored in the form of ones and zeros only. So each memory cell will store 1 bit of binary information or binary data or information. Okay, so there are 2 raised to n rows. 2 raised to n rows we have. and these are called as word lines, WL. Now on the rows we can call it word lines, and word lines we can call it rows interchangeably. Then it has 2 raised to m columns. These are called as bit lines. Okay, so the total number of memory cell in this array is 2 raised to n, 2 raised to m in cross 2 raised to n. Okay, so to access a particular memory cell, a particular data bit in this memory array, the corresponding bit line and the word line must be activated. So let's say if you want to activate column number 1, sorry for that. So let's say if you want to activate column number 1 and row number 1, that means you have to activate this memory location, which I'm showing in green color. So how will you select that? So you have to select that from the column decoder. So column decoder will select the address. So let's say B1 is the address, which will select one column line, one bit line out of 2 raised to m bit lines. So let's say it will select column number 1, and the row address decoder will select one of the lines, or one of the word lines from 2 raised to m lines, 2 raised to n lines. So your A1 will store the address of the, will point out to the address of the first row. So first column and first row we selected, and we access the first memory location. Okay, so that's how we select a particular memory location in this array, memory array. So row and column selection are done by row and column decoders. Okay, so we have a row address decoder. Here it is. This one is the row address decoder. So row address decoder will select 1 out of 2 raised to m word lines according to the n bit row address. So this is my n bit row address, which will select 2 raised to n, one of the 2 raised to n word lines. Okay, and then we have a column decoder, column address decoder, which will select 1 out of 2 raised to m bit lines. Okay, and this is my m bit column address. So here let me write m bit column address. Okay, so once a particular memory location is selected, data can be read or data can be write operation can be performed, okay, on one bit or multiple bits on a particular row. So therefore individual memory cells can be accessed from the data read write operation in the random order, independent of the physical location here. So it's an organization of a random access memory. Okay, so basically this is my RAM structure. This can be used for both read write memory array or read only memory array. Okay, so it can be used for both read write array, or it can be used for read only array also. So we'll be concentrating on ROM array. So this is can be used as a ROM array also, because to select a one particular memory location, then it depends upon whether we want to read the data or we want to write the data. Now we are only concentrating on the read only feature of the memory. So we will be concentrating on the read only memory or ROM array. Okay, so you have any doubt in this memory array organization? You have understood the role of a row address decoder, column address decoder, how to select, how to go to a particular memory location. Everything is clear to you, students? Quickly reply yes or no. Okay, very good. So now we go on to the next part. So here onwards, we actually start with everything else. So we go with ROMs, read only memories. Okay, so basically, so in the ROM, read only memory cells. So ROM cells are permanently fixed. Okay, they are at fixed locations. So we have several possibilities of designing the ROM, memory cells. So let's look at one example. Okay, let me look at one example. Please concentrate over here. So we have a bit line. Let's say bit line is, what is bit line? Columns or rows? Columns. Okay, and word line is rows. So remember that. So now I'll be using word line as, I'll be using WL for word line and BL for bit line. Please remember. So bit line means columns. and word line means rows. Just remember this forever. Now let's start. So let's say we have a particular, let's say here we want to store one information one. Okay, so let's say we have this is my word line, and this is my bit line. Now the cross juncture of them, I mean wherever they are intersecting, the cross point of them means there will be a memory array, memory core. So here is my memory core, let's say. Okay, here is my memory core. Now this can be a MOS transistor also, or this can be something else. Okay, so here is my information, here is my memory, which can access it. Okay, now there are different ways you can do this. So first is, let's say if you want to store information 1, logic 1 information, so you can just store this information by the intersection of bit line and word line, let's say. So this cross point will store that information. Okay, next we want to access 0 location. So 0 can be accessed as follows. Let's say you have a bit line, you have a word line. So wherever you have a word line, you connect a transistor to bit line like this. See, so its word line is connected to the gate terminal, bit line is connected over here, and this bit line is pre-charged. That means this bit line is connected to VDD. So now if this is connected to VDD, okay, a pre-charged device, which can be VDD, or it can be, during the other phase, it can be 0 also. So if that transistor is on, let's say it is connected to VDD. Okay. Now, when the this bit line is 1, let's say the bit line is 1. So bit line is 1. Whenever word line is 1, what will happen? What will happen? This transistor will turn on, and it will discharge the one which is stored over there to ground. Yes or no? So this will this one which is stored at the whenever bit line is 1 over here, and the word line is 1. Let's say bit line is 1 means this is connected to logic 1. So this is at VDD. Now word line is also 1. That means this will activate the transistor. But the transistor is on means what? Replace with a short circuit. Okay. So that means this will allow the information to go to logic 0. So here we have this NMOS transistor. NMOS provides the pull down part. Agree? NMOS provides pull down part. You agree or no? Hello? Are you all understanding, students? Hello? Yes or no? Okay, okay, sorry. Uh, yeah. So now, as I told you, this can be pre-charged. The bit line can be pre-charged. So the same information can be drawn like this. So pre-charged transistor means what? We can have a pseudo NMOS transistor like this. Okay? Whose gate terminal is permanently grounded. So this is my PMOS transistor whose gate terminal is permanently grounded means what? This PMOS transistor will always be on. Yes or no? So this you apply to the bit line. This you apply to the bit line, and other line you apply as a word line like this. So this is my word line. This is my bit line. And now you connect the transistor over here like this. Okay, to 0. This is connected, and this is connected to the gate terminal. So now this bit line, even if you don't give anything to the bit line, it is pre-charged to VDD. Okay, and this is a weak PMOS, as I have already informed you all during the pseudo NMOS logic style design. So this is a pseudo NMOS. Yes or no? Pseudo NMOS. Comparatively, this NMOS enhancement is my strong NMOS. Okay, so this transistor over here, please concentrate on this part, please, because this is very, very important, which I'm discussing. So this NMOS is the stronger one, which when activated will pull down the bit line to, pull down the memory location to 0. So it is used for storing 0. Okay, so logic 0. So NMOS provides, I've written there, pull down part. What does the PMOS do? The PMOS is used to hold bit line high. Okay, so please draw this. Whatever I'm circling, please draw this. This much information you draw, please. Yeah, please draw this in your books. Okay, I'll give you some time. Take few seconds and draw it, because it's very important, because based on this we have 4 cross 4 NOR base ROM array. Yes. We want, let's say for some application, we want the bit line to be high. Okay, now as you can see over here, this is programmable. This is permanently connected to ground right now. So that means this transistor is always on. That means it's always conducting. Yes or no? So whenever a transistor is conducting, it is replaced with a very low resistance part. So this as good as connected to VDD. Understanding? So that means bit line is 1 here. Bit line is 1 here. So now when the bit line is 1, but that can be a 0 also. Bit line can be pulled down to 0 also. But right now, if the word line stated is not clear to you, bit line will continue to hold the data 1 high. Now let's say word line becomes 1. Now when the word line becomes 1, NMOS transistor turns on and makes the bit line 0. Understanding? So it will make the bit line 0 by discharging like this. So logic 1 will become logic 0 now. Okay? Because NMOS is stronger. So it will provide the pull down part. Did you understand now? Yes, no? Okay, great. So now you have noted down this information? Sorry? You're asking something? Okay. So coming to the next slide now, this is the arrangement which I was showing you all. This is holding logic 0. There are many possibilities of it. Okay. So here we are not going through diode based ROM. This is not there. We are also not going for MOS based or based ROM. We are going for NOR based ROM. Okay, so this means a cross junction of word line and a bit line means what? Logic 1. It will store logic 1. And whenever this transistor is on, and the bit line is high, we can store logic 0. So this is what we are going to use it now. Okay, so this corresponds to logic 1, this corresponds to logic 0. So that's why it's called as a MOS transistor NOR based ROM memory cell. Why NOR? Can you tell me why NOR? NOR means what? A, B, A plus B, A plus B bar. So 0, 0, 0, 1, 1, 0, 1, 1. So it will store 0, 1, 1, 1. It will store 1. Here it is. So we'll understand the meaning of NOR base ROM pretty quickly. Don't worry. Understood this? This means corresponding to logic 1. This means corresponding to logic 0. Now this is the same thing which we had, same slide but with more details. We are not doing this, here. This is important. Now see this. Bit line is pre-charged to VDD. Now do you understand? This will be more clear. Let's say bit line is pre-charged to VDD via the PMOS transistor, pseudo NMOS transistor. Okay, as shown over here. A weak pre-charge. So it's pre-charged to VDD unless specified. So bit line is 1. So when the word line is 1, it will store logic 1. Okay. Now, bit line is precharged to VDD. Now, when the word line becomes 1, uh, what will happen? The bit line will store grounded. I mean, 0 information. Yes or no? Understanding? Yeah. So we have 1 when the bit line is grounded, and we have a 0 when the bit line is VDD. Yes or no? Understanding? Okay. Now we design NOR base ROM array. So write down the question, everyone, as they will ask you in the exam. I'm making you write the question. Design and implement a NOR based ROM array that stores the following information. Okay. Let me see if we have one more page we have. So this is the information given to you. Uh, the information is as follows. These are rows information. That means what? Rows means bit line or word line? Yes. Rows means word line and bit line means columns. So these are nothing but word lines. So we can also write it as over here WL0, WL1, WL2, WL, interchangeably. So this information can also be given. Then we have here write C1, C2, C3, C4. So this will be corresponding to which data? Bit lines. Okay. So let's say in the row format, it stores the information in this form 100. So that means row 1 is activated. Okay. Rest all are zeros. So row 2 is activated. In the third case, row 3 is activated. In the fourth case, row 4 is activated. Similarly, C1 to C4. So column, let's say we want to store this data in the bit lines 1, 0, 0, 1, then 0, 1, 1, 1. We want to read this particular data. So how will be the arrangement we will write? So please note down this data. So basically, right now I am still in college. So we'll do this design and I'll take a break. And then I again reach home. I'll again restart from where I've stopped. Okay. All right. Let me complete this topic and then we can. Are you ready? Can we? Have you written the data? Yes. No. What? Okay. Sometimes they even give you the data in different form. Let's say I'll tell you how differently they will give it to you. The row details can be given as, for example, this is an example 1000. Sometimes they don't give the row details at all. 0100, then 0010 and 0001. Sometimes they give in this information and the column details are. You understand what is this in a decimal form? 9, right? First one, second one, in decimal how much it is? 0, 1, 1, 1, 7, right? Then this one is 6. And the last one is 1 in decimal. They might give you in this. They might give you the information in hexadecimal also. Okay, so number of columns will increase then. This is just the 4 bit lines. Or sometimes they give you this information. They go ऐसे, word line 0, word line 1, word line 2, word line 3. Here I am showing you how differently they give the information. Word line 3. Then we have bit line 0, bit line 1, bit line 2, bit line 3. It all means the same. So it means 1, 0, 0, 0. These are the different ways in which the data can be given. This can be in hexadecimal also. So please convert it into binary form. 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. Then here we have same information can be presented like this. Okay? Understanding? Yeah? Can we begin now? So these are the different ways in which the same information can be given to you. Now let's start with the design. So this is called as, since it is a 4 cross 4, it is called as 4-bit cross 4-bit NOR based ROM array. It is 4-bit cross 4-bit NOR based ROM array. Okay. Now can we start with the details? Alright, let's start with the design. So first of all, you have to draw the pull-up transistors. You remember, first you draw the pull-up, the pseudo NMOS. So here it is, the pseudo NMOS transistors, like this. Okay, individually you can connect it. So this is VDD, 4 of them, because this is 4 cross 4, and you connect them. So these are used for pre-charge phase. These are all weak PMOS transistors. So whenever a particular NMOS transistor is on, that will pull it down. So these are all called as pull-up devices. All of them have connected to the same VDD. So I can connect a similar VDD to them. Okay, this is my VDD. Alright, now I'll extend these lines below. Extend these lines below. So call this as C1, C2, C3, C4. Okay, these are the bit lines. Alright, and draw 4 horizontal word lines. So here is the first one. So here are my word lines. Row 1, I have to draw a little closer. Row 2, row 3, and row 4. Can I extend this down a little? Yes, I can. So this I can extend a little down. Please draw along with me. So again, these are the bit lines C1, C2, C3, C4. And what are the word lines? R1, R2, R3, R4. So these are my word lines. Okay. Don't put any, this dot over here around. Now tell me which information is stored. What is my column details? C1, C2, C3, C4, C1, C2, C3, C4. So first, we already know is the first column gets selected. Sorry, first row gets selected. But what is the information there? Can you tell me? 1001. Correct? Are you paying attention? So wherever there is a zero, listen carefully. Wherever there is a zero, add a transistor. So where there is a zero, C2. So C2 may you add a transistor like this. Here it is. Understood? And this will be going to ground. Here you dot. So wherever there is a zero, so C3 also there is a zero. So add a transistor. We'll see it's working shortly. Now next number was, can you tell me the next data? Next data in line is for row 2. Come on, tell me fast. Yellow there. 0. So where is the 0 stored? At column 1. So column 1 will be connected to the ground. Connected via the transistor here. Like this. Okay. Connect the. Next is 0, 1, 1, 0, right? So where are the transistors connected? C1, here it is. And C4. Where is C4? Here. Okay. Last case is 0, 0, 0, 1. So there are 3 transistors now. Here. Here it is. Then we have another one over here. Sorry, I should have more space over here. And 3 also, right? Here also, no? What if there are all ones, then no line is selected there? You don't connect anything there. Okay? So this is the design. That's it. This is my 4x4 NOR based ROM array. Now let's see it's working. So here, let me also write R1, R2, R3, R4. So here there is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Now how this works? Anyone? Okay. So all the bit lines are pre-charged to VDD first, if the word lines are not activated. So initially all the C1, C2, C3, C4 are 1111. Okay. Now let's say the first row is getting selected. First row is getting selected. So we have R1 as 1. Here it is 1. Let me use this green color now. This is 1. Okay, now what will happen? Now what will happen? So this transistor will get activated, yes or no? This transistor will turn on. Hello, are you listening? So this is connected to C1 is connected to 1 only. C1 is 1 only. I told you initially all these are 1111. Now row 1 means R1 1 means what? This transistor is on, that means it will be going to the ground. This C1 will go to the ground. So C1 will be becoming 0 now, right? 0. And also this one more transistor is there, right? This also will get activated and this will be discharging towards ground. So C3, this bit line will be 0. So it will go to 0. So we have what information now? 1001. Understood this? Yes? Now again we'll go back to the stable condition. Now we'll go to row 2. So row 2 is activated over here, whereas all the other rows are 0, 0, 0. So no need to write also, right? So now row 2 is activated. It is 1 over here. So this transistor is on. So that means C0, C1 will be 0, right? Rest all are 1 only because they are all precharged to VDD. So 0, 1, 1, 1. Now let's check the next case. Row 3 is 1. Row 3 is 1 means what? These two transistors are, this bit line will be, C1 will become 0 and C4 will become 0 because these two transistors are activated. So now this will become 0, this will become 0. So the information will be 0, 1, 1, 0. See, 0, 1, 1, 0. Agree? Yes or no? And the last bit of information will be, let's say row 4 is activated. So row 4 is activated means what? There are 3 transistors which are activated like this, 1, 2 and 3. So these 3 bit lines will be becoming 0. This will becoming 0, 0, 0 and 0. So the data will be stored will be 0, 0, 0, 1. Here it is. Understood? So this is the working and the design of 4x4 NOR based ROM array. Okay. Now, understood the design technique? If they give you any information over here, if they give you any information, can you do it easily? It is very, very easy topic, a scoring topic. They ask you for 10 marks. So can you complete this design? Design and implement a NOR based ROM array that stores the following information. Okay. Now this information can be in decimal form, binary form or hexadecimal form. If that is in hexadecimal form, it will go to for 8 columns. So no problem, increase more number of columns over here. Rows will let it remain 4 only. Okay. Understood this design? Everyone tell me, give me a response. Okay. So what are we left out is, now I actually have to leave the college now. So what I will do next is, I will be revising this with another example. Then I will be teaching you this in more details with a smarter design. Then we'll be studying about pre-charged MOS, this thing. That means this was permanently connected to ground, right? We can connect it to from ground to 1 also. So we can avoid the static power, dissipation here. Then we'll do the NAND based design, NAND based ROM array. And after that, we will do the design for row and column decoders. So once we do the design for row and column decoders, you remember in the memory array, we are designing 4x4 NOR based ROM. We will be designing 4x4 NAND based ROM. But what about the memory array? What about the address? This one, let me show it to you. This one, we are designing this network easily. Okay, but what about a row address decoder, column address decoder? So that also designing we are remaining. So 3 more designs are remaining now. Which all designs are remaining? We have completed NOR based ROM array. Now we are NAND based ROM is remaining. Then row address decoder design is remaining, and column address decoder design is remaining. Okay, so that will continue in the second half of the lecture. All right, so let me stop the recording now.